We often like to argue about who's right and whose opinion is more important, but you see, in science, we can't really do that. We have to rely on the scientific method, which means we'll make some kind of an observation. So let's say we're growing some plants, and we notice that when we fertilize some of the plants, they grow much bigger than if we don't fertilize these other plants. Those grow much smaller, right? So we're going to make a hypothesis here. And now the hypothesis has to be a falsifiable prediction. So that means you have to be able to design an experiment that can prove you either right or wrong. So that means, let's take 6 weeks of time and let's give these plants over here fertilizer and not over here, and then we'll repeat the experiment, and then this time we're going to give nothing fertilizer. So that way it's, So this kinds of stuff will set up a type of experiment that you could prove yourself right or wrong. And then you're going to be able to eventually set up these experiments, essentially, that will prove you right or wrong in your hypothesis. And if you do this enough times, you're going to be able to come up with this thing called the scientific law, which is essentially an equation that describes the patterns that we see. And this essentially just says what happens. So let's say we have the force of gravity, right? We got two planets, and they're basically F equals G times mm over r squared. This is an equation that'll describe what happens when two things are pulled towards each other. Well, then we have this thing called the scientific theory, which is essentially trying to explain why this equation even exists. So it's actually usually a collection of laws, collection of different equations, and a lot of evidence, tons of evidence that will explain why these equations exist. Explain why they exist. So for the force of gravity, we've sort of realized that it's the curvature of space and time that actually, space-time, curvature of space-time that causes that equation to even exist. So this is what the scientific method is. Now, since this is chemistry, we should know what chemical energy is referring to. That's just trying to describe the potential energy stored in the chemical bonds, the bonds between the atoms. We should also know the two laws and theories that are pretty important for us. Energy and matter, both of these, the conservation law applies. So they cannot be created or destroyed, which means that on both sides of chemical equations, you're going to have the same amount of stuff. And for the atomic theory, this is also important because it just says that all matter is made of atoms. And that means that we can use the periodic table to essentially figure out what anything in the world is made of, which is really cool. Now, all these atoms are actually going to make matter, right? So let's look at matter. We got states of matter. Solids will basically just have a whole bunch of atoms just jam-packed into a block right here. Liquid is going to be a little bit more sparse, but still quite a bit. And a gas will essentially just be a couple of particles here and there, so it's going to be much less dense than all these. And this is going to be the solid. This one is the liquid. This one is the gas. Now, if we were to compare the shape and volume of the solids, liquids, and gases, we would notice that the solids can't change shape, they can't change volume. The liquids can change shape, but they can't change the volume. And the gas can change both the shape and the volume. And we should realize that most of the time, the atoms are going to be rearranged in either a crystalline or an amorphous structure. And the crystalline will have really tight bonds here, so it'll make it harder for this to break apart. Now, matter can appear in three different compositions. You would have elements, which is essentially a pure form, or you could have a compound. Both of these are pure. That means that we would simply have one element in this. You could have a bunch of them, but there's just going to be one kind. And in the compound, you might have two elements, okay? But at the same time, you might have a whole bunch of these things. So you might have a whole bunch of elements, the same element, or a whole bunch of these compounds, but it's the same compound. That would be a pure composition. We also have this thing called the mixture, which is essentially going to be a combination. We're going to have some of these sitting in there, and we're also going to have some of these other ones. It's just going to be a blend of stuff. Now, we can try to separate out these mixtures and pull them apart. We could use filtration, we could use distillation, we could use decanting, centrifuge. And there's two kinds of mixtures that we might encounter. The homogeneous mixtures, that would be something like salt plus water. If you combine those two, it'll be just, it looks like it's a solution, a normal solution. You could also have a heterogeneous, and that would be something more like oil and water, where you're going to actually notice visible differences in that compound, that the oil is going to stand out from the water, so they're not going to really combine very well. So that would be the mixtures. Here's a couple of properties of matter. We would have physical properties that could be measured without interfering. And so this would be something like density. You could just measure the mass, measure the volume, and you wouldn't mess with the compound. Chemical properties can only be measured by changing the compound. And so you could measure something like reactivity. You'd have to put that through some sort of a chemical reaction to be able to measure the chemical property. You also have intensive and extensive properties. Extensive things basically depend on the amount of the substance, so this would be something like mass. But an intensive amount would be something more like a ratio, where it doesn't change when you change the amount. So it doesn't depend on the amount because it's a ratio, something like temperature. Doesn't matter how much you have, you measure it, it's going to be the temperature of whatever it is. Now, substances can undergo changes, both physical and chemical changes. Physical is more like altered state. This would be shifting through these different states of matter. It would be the same compound. So it would be like from ice into water. And during that whole process, it's always H2O. But a chemical change would result in a new chemical compound. So this would be something like N2 gas combines with some hydrogen gas, and that basically turns into 2NH3, which is ammonia. So that whole thing, we've got three different compounds that are sort of changing into something, even though you think, hey, you've got N's and H's, but it's a different compound. Dimensional analysis can be pretty helpful because we might need to make some unit conversions, and essentially we're trying to make sure that both sides of the equation have the same units. So we'll try something like miles per hour times hours over minutes. These hours will cancel, we'll get miles per minute. Let's continue though. We'll make this over kilometers per mile. And we're converting miles to kilometers there. We'll get rid of these miles so that way we get something in the end, kilometers per minute. Now the cool thing about dimensional analysis, you can see this is a pretty long equation here. So this allows you to not have to round a whole bunch of times. You just round one time at the end. So you'll have one equation and one solution. And try to make as long of a chain as you can so that way you can round at the end. And that's great. Now, you might have to break these up at some point, so that's why, it's good to use fraction form. So that way you don't have to get any long decimals, or run on decimals, which would be even worse. And over here, you might want to mark decimal places if you have to work with decimals, at least mark how many significant figures you're going to need to count. We'll get into that in just a moment. But this is all so that you can round at the end and get the correct amount of significant figures. Now, experiments aren't perfect. They're going to go wrong, so we're going to have some errors. We'll have random errors or systematic errors. And the random errors are essentially unpredictable. This is uncontrollable and kind of natural fluctuations. Okay, but systematic error would be something that's predictable. It's consistent. It's repeatable. So you can control systematic errors. Now let's compare precision and accuracy. Because precision is going to be how many times can you hit the same spot or really close to that spot. But the accuracy is going to be if you have a target here, how close do you come to the target? Both of these things are important in experiments, but sometimes it can be easy to confuse them. Now let's get into everyone's favorite topic, the significant figures. Let's say we have 1, 2, 3, 4, 5. These 4 are going to be certain, and this last one is going to be an estimated digit. We have 5 significant figures in total. And we really only care about these significant figures when we're dealing with measured quantities, when we're sort of manipulating them in some way. So let's say we're multiplying or dividing measured quantities. We're going to focus on the least number of sig figs. So let's say we had a 3.0 multiplied by 2.22. This one has 2 significant figures, therefore the answer is going to have 2 significant figures. This one has 3. We're focusing on the least number of significant figures. But for when we're adding and subtracting measured quantities, then we're going to focus on the least decimal places. And so if we have 3.0 plus 2.22, the least number of decimal places here is 1, so the answer is just going to have 1 decimal place. Now let's say we're trying to read this thermometer here. See, it's 2, 3, this is 2.5 here. Since we have a 2.5 being a for sure, that's a certain, then we can estimate whatever it is here. Like, if I really wanted to, I could call that like a 2.2 or something. But if I really wanted to, I can call it like a 2.8 if I really wanted to. Depends on your perspective. So we'll go with a 2.56 and we'll just call it a day. But the idea here is that we're allowed to take our for sure, and then we're going to move estimate 1 past that line that you get. All right, so you got 2.5, estimate 1 more digit past that. Now if we're rounding, then let's say we have a 2.4, this rounds down to become a 2. And if we have a 2.5, this will round up to become a 3. If we have to round that, 4 goes down and the 5 goes up. Let's take a look at the zeros situation. Well, if we have a whole bunch of zeros on the left, doesn't matter if there's a decimal. We're just going to go for the first time we see those numbers, and we start counting significant figures from the first real number. Over here, this one here, if you have a decimal, you're going to count all the zeros to the right of the decimal. So this one, you're going to count that one, and then you get 1, 2, 3, 4. So 4 significant figures here. And then this one, we got 500 with a dot right there. I guess you can kind of think of this dot like a period. It's going to tell you how many significant figures you have. 1, 2, 3. Over here, you're just going to use 1. Because if you don't have a dot, then all the zeros to the right will basically just go away. I guess the best way to put this is that zeros on the left don't mean anything at all. And the zeros on the right only mean something once you have a decimal there. If there's no decimals, then all the zeros on the right don't matter. Like this one right here, you just take that 1. This one actually has 2 zeros involved with that decimal. This one has like 3 zeros involved with that decimal. We also have this other thing called exact numbers, which are kind of interesting because they have an infinite number of sig figs, which means that you can essentially disregard them from these calculations they're going to have an infinite number of significant figures. We're always focusing on the least number of significant figures. So you always want to focus on your measured quantities. Those will always be the bottleneck in these equations. So these are going to be things like counted items. Let's say you have 5 bottles. You might be thinking 5 is a very small significant figure. It's only one significant figure, right? Nah, this is actually 5.00000 with an infinite number of zeros. So that's actually infinite significant figures right there. We also have defined numbers. Something like a dozen, that is going to be equal to 12.0000 infinitely. And we also have this conversion factors, like for example, inches to centimeters. Any kind of conversion is going to actually be infinite number of significant figures as well. So these are exact numbers. Lastly, let's try to figure out the significant figures for logarithms and exponents. So let's say we had a logarithm, and you're going to have some significant figures inside that logarithm. It's going to give you an answer dot sig figs. So if that didn't make sense, let's say you had logarithm of 1.23. You got 3 significant figures inside there, so you'll have some sort of an answer over here to the left of the decimal. Let's just call it a 5. But then here you're going to have your 1, 2, 3 significant figures. You're going to make sure that the left side of the decimal doesn't matter, and your significant figures go on the right of that decimal. If we have 10 to an exponent, and then there's going to be a period there, we're going to count the sig figs. We're going to really count all the digits that are included past that decimal. So you're going to include the zeros in those sig figs, counting all those. That's going to be equal to the total number of sig figs on the other side, including that decimal. Now what this means here is an example: 10 to the 5, that's the exponent, dot 0, 1, 2, 3, 0. If we count all those, including the zeros, that is 5 significant figures. Therefore, the answer will be 1.2345 with 5 significant figures. And there we go.